Close to expiry.
Okay. So which one is close to expiry? 6 month or 1 month?
One month.
One.
Okay. So now you understand, right? So if you have a 6-month option, okay, let me put this here. Let us put these here, delta, vega, and gamma. Okay. So if you have less time to expiry, or you have less time to expiry, okay, then gamma will be dominant. Okay, and if you have more time to expiry, then vega will be dominant. Okay, I hope everybody understands this. Okay, so we have pretty much covered the yesterday's leftover portion, right? You can continue with short positions and all other things. Okay, yesterday we were discussing delta of a short call. So let us see how it looks like, or can we even see that? I don't know. Yeah, so this is how delta of a short call looks like, and all of it is in negatives. Okay, you have to see this. This is important. This is in negatives. So, and so on and so forth. Okay, so I hope you make use of this script well to understand and study Greeks. Okay, and this is how you should study graphs. Okay, at least in context of Greeks. So you should always look at levels, slopes, and curvatures. Okay, so what's happening to slope, to level, or to curvature? So this is week 3. Weeks index. Now let us get back to a little bit of math. So today we'll see derivation of Black-Scholes PD. Black-Scholes PD. Okay, and let us see what all basics we require for that. Okay, so we are going to hardcore stochastic calculus now. Okay, the stochastic dynamic which is used for evolution of stock price. Evolution of stock price. Okay, it is described by geometric Brownian motion. Which is given by ds by s is equal to mu dt plus sigma dwt. Okay, yesterday we saw simulation of arithmetic Brownian motion. Which is given by ds is equal to mu dt plus sigma dwt. Okay, can someone tell me difference between this and this?
In the denominator, S is available on geometric.
Correct. That is kind of mathematically what you see, right? But what is the meaning of this versus this? Okay, what does ds represent?
Geometric Brownian motion will change in terms of log, I think, and
But
if
why do you, but where do you see log function here?
like if we integrate ds by s.
Okay, that is kind of so you need to do something on it mathematically, right? So you need to integrate it. Okay, even before integrating, right? As is the way I have written these statements. What do they mean or how do they differ? Okay. So what is DS? DS is
Change in stock price.
correct. So this is change in stock price. Okay. Now change in stock price is described as, so mu is a constant, correct? So this is a number 10%, 15%, something. This is expected average growth rate of the stock, which we discussed yesterday. Delta T is also constant, so that depends on your discretization interval. If you take 1 day as a discretization, then your time to, then your DT will be 1 divided by 365, correct? So these two are constant, right? The the change or the uncertainty in the stock price comes from the Wiener process, something which is normally distributed, right? So the change in, so if I ask you the change in stock, what is the distribution of change in stock price in arithmetic Brownian motion? What will be your answer? What is the probability distribution of change in stock price in arithmetic Brownian motion?
Normal distribution.
Right. So this is change in stock price, right? So let us say this is some number. Okay, so this is C. Okay, now mu is constant. Okay, so this is A. This is also constant. Let us say B. Okay, plus sigma is also a constant. Okay, and dwt can be written as square root of t, okay, dt in this case, multiplied by a random variable, okay, which is standard normal distributed, correct? So whatever is distribution of this is distribution of this, because everything else is a constant, right? So everything is just scaling factor. So distribution wise this is same as this, right? So arithmetic Brownian motion says that change in stock price is normally distributed, correct? Now let us go to geometric Brownian motion. What is ds by s?
Change in stock price by original stock price was.
Yes, what is that called as? If I tell you the answer, you it will click. You'll say that yes, this was too obvious. What is
Is
change in
delta.
delta of what?
Uh, delta of no, no, no.
Delta is defined as change in option price. We are yet to go to option. We are just sticking to the stock for now.
Okay, okay, sir.
This is change in price. So if I tell you, okay, stock price is at 100. Okay, this is ST. Okay, and ST plus delta T is 110.
That is a return, sorry. Return.
Exactly. This is how you should think about things. Okay, you should put in values and you should then it will click. So this is returns. Okay. So earlier we have seen change in stock price is normally distributed. What does geometric Brownian motion tell us?
Returns are normally distributed.
Yes. So here you can say that returns are normally distributed. Okay. And in turn, when you integrate it and do all of that, right, then you will see that log of S is normally distributed. That is why S is log normally distributed. I hope everybody understands what I'm saying. This is where the property of stock price comes, that stock price is log normally distributed because returns are normally distributed. So you can pick any stock, you can calculate its historical return, and you can try to see what kind of bell curve it shows. Okay. And this is why we use a geometric Brownian motion for simulation of stock prices. Okay. So now let us look. So let us look at a portfolio. Okay. Now I have a portfolio, let us say pi, okay, which is collection of an option. Okay, so one long option, and I have shorted delta numbers of shares. Okay, and let us see how this portfolio evolves in time. Correct. So for example, I have one long call on Nifty. Okay, and then I have sold X number of shares of Nifty. Okay, so that is our portfolio, and we are seeing how this evolves over a period of time. Okay, so before that we have few preliminaries. We have ds by s is equal to mu dt plus sigma dwt. Okay, so mu is stock specific. Okay, so you need to find mu separately for each and every stock, because every stock has a different rate of growth, right? So if you have to simulate the stock price of a particular stock, then you need the average growth rate of that stock. Okay, that is mu. Okay, now what is d pi? Okay, so d pi is equal to df minus delta times ds. Why? Because delta is a constant number. Okay, s is changing, option price is changing, and your correspondingly portfolio value is changing because of that. Okay, so now let us take a look at this. Okay, so f is your option price, right? So this is equation 1. Okay, so f is essentially a function of underlying stock and time to expiry. Okay, now stock itself is a function of a Brownian motion or a Wiener process. Okay, let us keep that in mind. Okay, so df is written as dou f by dou t into dt plus dou f by dou s into ds plus half of dou square f by dou s square into ds square plus half of dou square f by dou t square into dt square. Okay, this is simply called as Taylor series expansion of a function. So we have been discussing partial differential equations ever since. So I have given at least 2 assignments on these partial differential equations, right? So whatever variables are present, okay, first you take first derivative with respect to that, okay, partial derivative multiplied by total change plus partial derivative with respect to second variable multiplied by total change plus half of second derivative with respect to first variable multiplied by square, and so on and so forth. Okay, there are higher terms also, but they are of the order 0. Okay, so that is essentially 0. Any questions so far? No. So now let us look at this. Okay, so you have df is equal to dou f by dou t into dt and so on and so forth. Okay, so now let us look at the term ds square. Okay, now dt square, the term dt square is also, it also tends to 0. Okay, because dt is a small term, so dt is a small term approximately, I mean it tends to close to 0, so dt square definitely goes to 0 at a much faster rate. Okay, so this is also of the order of 0, right? So what are we left with? We are left with ds and ds square. Now before we proceed, let us calculate what is ds square. ds square, okay, is equal to, what is ds in the first place? ds is equal to mu s dt plus sigma s dwt whole square. So this comes from this equation. So I'm just substituting ds is equal to mu s dt plus sigma s dwt into this equation. Okay, so this ds is equal to this. Okay, and then squaring it up. Okay, then what we get, this we get as mu square s square dt square plus sigma square s square dwt square plus 2 sigma s mu s square dt dwt. Okay, now we have just seen that dt square is 0, so this term goes to 0. Then we have seen that, so dt into dwt, it is, so dwt is equal to square root, so dwt is equal to square root of dt. This we have seen from quadratic variation assignment, right? Therefore this becomes dt to the power 1.5. This is dt power 1, this is dt power 1. This is dt power 0.5. Okay, so this becomes dt power 1.5. So dt to the power of anything more than 1 tends to 0. Okay, that is why this also tends to 0, and hence we are left with sigma square s square dwt is square root of dt, so dwt square is dt. Okay, so this is ds square, sigma square s square dt. Okay, any questions so far? When you have your normal calculus, there even this term goes to 0. Okay, but since this is a Wiener process, this requires a different kind of calculus, which is stochastic calculus. This term does not go to 0. Okay, and why it does not go to 0? Because of quadratic variation, okay, which we have seen earlier. Okay, so this is ds square. So we have established ds square, let us say 3. Then we have df, which is expansion, which is equation 2. Now we have this and this we can substitute directly, right? So what is df? Okay, so let us go step by step. df is equal to dou f by dou t into dt plus dou f by dou s into what is ds? ds is equal to mu s dt plus sigma s dwt, right? Plus we have half of dou square f upon dou s square into ds square, right? And the term for ds square, we just derived it, that is sigma square s square dt, which is sigma square s square dt. Okay, so this is the equation for df. Okay, now we substitute equation 4 in equation 1, right? And let us see how the portfolio evolves over time. So dou pi is equal to, okay, you have df is dou f by dou t into dt plus dou f by dou s into mu s dt plus sigma s dwt plus half of dou square f by dou s square into sigma square s square dt minus delta times ds is written as mu dt plus sigma dwt, correct? Now, okay, now we have this equation. Okay, now as discussed earlier, in any price process, okay, what is the source of uncertainty? Can someone tell me what is the source of uncertainty in a price process? Anyone on the call?
So volatility.
So volatility is a constant number, right? Volatility is just a constant number. You can treat that as a constant number. Okay, so consider this as a price process. Okay, this is price process of stock returns. Okay, why is there an uncertainty in the returns? Because of which term? What is constant and what is not constant?
DT and DWT are not constant.
dt is constant, right? dt is equal to your time increment. Okay, so if you have a timeline of 1 year, t equal to 1, and you divide it into small parts, okay, this is dt. Okay, so your dt as a number is equal to, if you have divided t into n parts, this is your dt, correct? So if you have divided 1 year into 365 parts, this is your dt. Okay, so each time in each of your simulation, your dt is going to be fixed, correct?
Yeah.
Mu is also fixed, correct? Because you take 10%, 15%, whatever. Okay, volatility is again assumed to be constant. This is one of the assumptions of Black-Scholes model. Okay, so this is 15%. Okay, so what's the source of your uncertainty? It is DWT, right?
But sir, it is a under root of dt. So why it is
No, no,
uncertain?
no. DWT is not. So DWT is a Wiener process, right? So Wiener process is normally distributed, right? Just now we saw, right?
Yes, sir.
DWT square is equal to dt. Okay.
Okay.
So this is normally distributed. DWT itself is normally distributed. Okay. DWT is not a constant, right? DWT, the way we simulate is, so we'll write sigma into square root of dt into normal, correct? Okay. Therefore, your source of risk, why will your this portfolio has a risk? What is the source of that risk? The source of that risk is DWT, correct? So how do I make this portfolio risk free, or popularly called as risk neutral? How do I eliminate risk from that portfolio?
Sir, by removing DWT terms.
Correct. So whatever is the coefficient of DWT, if you set it to 0, then this portfolio becomes risk free, correct? Now let us do that. So if you have dou f by dou t into dt plus, okay, dou f by dou s into mu s dt, okay, plus sigma s dou f by dou s into dwt plus half of dou square f by dou s square into sigma square s square dt. Okay, this I have written as it is, minus delta times mu dt, okay, plus delta times, sorry, minus delta times sigma into dwt. Is it right? Please check for the signs and everything. So we have this, then we have this term, then we have this term, okay, plus half of dou square dou f square by dou s square sigma square dt minus delta mu dt minus delta sigma dwt, correct? Now if you have to eliminate risk, we have to eliminate dwt. Okay, where is dwt present? It is present at only two places. It is present here and it is present here, correct? So if you see the coefficient of dwt, so it is present here and it is present here. Okay, so what is the coefficient of dwt? One is this and one is this, correct? So how to set that to 0? So sigma s into dou f by dou s minus delta sigma is equal to 0. I think we missed out something. We missed out one s here. Why did we miss out S? Because this was delta into ds, and ds is equal to S into mu dt plus sigma S into dwt. Okay, so we had missed out that S here. So I add back that S, which is S here. Okay, and add S here and S here. Okay, so sigma gets cancelled out, S gets cancelled out. So delta is equal to dou F by dou S. So when you say delta is equal to dou F by dou S, right, your uncertainty of your process goes away, right? Everybody convinced on this? So let me choose such delta. Okay, I have chosen delta is equal to dou F by dou S. Okay, if that happens, then I eliminate out this term is eliminated out, right? But this still remains. Okay, now let us see what happens. So you have dou F by dou T into dt plus dou F by dou S into mu S dt plus half of dou square F by dou S square sigma square S square dt. Okay, and what is left? Minus delta mu S dt. Okay, now if I replace this delta with this delta right, this becomes dou F by dou S into mu S dt, correct, which is same as this term. Okay, so this term is same as this term with an opposite sign, correct? So this term also get eliminated out. Okay, and you're left with dou F by dou T into dt plus half of dou square F by dou S square into sigma square S square dt. Okay, so we tried to eliminate only the dwt term. Okay, but the mu term automatically got eliminated along with it. We did not try to eliminate mu, but it automatically got eliminated, and this has very very important implication. Okay, can someone tell me what is the implication of mu getting eliminated? Okay, let us come back to this. This is mu, correct? Dou S by S is equal to mu dt plus sigma dwt. What we had discussed earlier, to simulate the returns of the stock, what do you require? You require mu, correct? Without knowing mu, you cannot simulate a stock price. But as a part of derivation, what we have seen is for the riskless portfolio, okay, of pi. Okay, for the riskless portfolio of pi, you don't require mu, correct? Mu is stock specific. So no stock specific growth rate related information is required for finding the change in price of a portfolio where a stock has been hedged perfectly by an option, right? That riskless portfolio just grows at a risk-free rate, right? I hope everybody can follow this. This derivation is very standard, and you will find it even on Wikipedia and Black-Scholes. So this derivation is very standard, okay? And sometimes they directly take dou v by dou s to begin with, okay, and which is kind of uh, not a good place to start, because then you don't get why do we start with that, right? And hence to avoid that, we actually went through the process of finding what should be that delta so that your winner process gets weeded out, okay? And then okay, and then after you after this, okay, it's just a riskless portfolio, right? So d pi is simply a riskless portfolio. So riskless portfolio grows at risk-free rate, okay? So d pi by pi is equal to r, okay? And then you just okay, just couple of steps, and you get this final equation, okay, which is famously called as the Black-Scholes PDE. Okay, note that. Okay, let me just write it down. Okay, so dou v by dou t into dt plus half of dou square f by dou s square into sigma square s square dt. Oh, okay, dt is not there. Okay, that's not required. This gets okay, and we had used notation of f for option. Okay, plus rs into dou v by dou s minus rv dou f by dou s minus rf is equal to 0. So this is your famous Black-Scholes PDE equation. Okay, so far so good. What we have done is define the problem. Okay, Black-Scholes did not get a Nobel Prize for deriving this PDE. I mean, of course, they also got it partly for that, because they came up with a riskless portfolio concept, hedging out winner process, and all of that. But the bigger stake is, of course, solving this PDE. Okay, they solved this PDE analytically and gave a closed form solution, which currently is kind of out of scope of our course, because as you can see, this derivation itself is so technical. If we sit down and solve it, okay, so there is a solution for that as well. Okay, if you can go on Wikipedia and see, there is a solution for that as well. Okay, so you will see that this, once solving this PDE, gives us the price of an option. Okay, so it gives a direct closed form formula where we can input all the same things. If we solve this, then we get something like this. Okay, so once you solve this for f, once you solve this, okay, then you get f is equal to, okay, n d plus times of s minus k into e to the power of minus r into time to expiry into n d minus, okay, and d plus is given by log of s by k plus of r plus sigma square by 2 into time to expiry divided by sigma into this time to expiry. Okay, so this is your d plus. When you take this is cumulative normal distribution of whatever number you get here, and d minus is equal to d plus minus sigma into square root of tau. Okay, all these things you will find here in the script which I have shared. Okay, so you'll find d1, you'll find d2, you'll find nd1, which is normal CDF of d1, and then you'll find normal d2, and so on and so forth. Okay, so if you put all the values, okay, you get the price of a Black-Scholes option, long call option. Okay, any questions so far? Any questions from anyone? What we'll do is we will just take a short 10 minutes break and we'll reconvene for the next part of today's session. Okay, I'm just going on mute for the next 10 minutes. Yeah, hi everyone. So I'm back, and I think while we wait for the folks to join back, uh, let us just refresh as to where we are, right? So far, so good. We have seen 3 ways to price an option. We have seen 3 ways to price an option. Okay. So the first way to price an option we saw yesterday, using binomial tree to price an option. Second, we also saw yesterday taking expectation of payoff. Okay, and discounting it appropriately, right? And third way we saw today of Black-Scholes formula for vanilla option. Okay, and the formula is call option price is equal to S into ND1 minus K into e to the power minus R tau minus tau into ND2, where D1 is equal to log of S by K plus R plus sigma square by 2 times time to expiry divided by sigma times square root of tau. Okay, and D2 is equal to D1 minus sigma square root of tau. Okay, so if you put all the values of S, K, R, sigma, time to expiry, and use this cumulative normal distribution function, you can directly find the price of an option. What is this? This to be n of d2. Okay, so far so good. We have seen these 3 ways to price an option. Okay, any questions so far? Any questions so far? Any questions? Jaydeep, Ramkrishna, Shivam Verma. Any questions? Sheikh?
No, sir.
No, sir.
So now you'll be able to price an option using these 3 methods, or you have doubt as to how to do it? If something is unclear, you can let me know. You'd be able to price an option now? So we will see as per our content, right? Let me just check what is now left to cover in terms of options. So yeah, we need to see exotic options. Okay, so let us go to, just rename this. This is week 3. This, and let us go to exotic options. Okay, so exotic options differ from vanilla options on the basis of the payoffs. Okay, so exotic versus vanilla options. Okay, so they differ on the basis of payoffs. Differ in payoffs. Okay, so let us look at the name of those options and what their payoffs are. Okay. For example, if you have so American option. Okay, the American option is an option where you can exercise before the expiry of the option. Anytime up to the expiry of the option, you can exercise it. So that's how it differs from a regular vanilla European option. Okay. That is American option. Then you have digital option, and there are two kinds to it: cash or nothing, or asset or nothing. Okay, so what it says is, if on expiry, so if S is greater than K, so okay, then your payoff is cash equivalent of a payoff, right? Of a fixed payoff. Okay, let us say that is like M. Okay, if not, so if not, it's 0, and same for asset or nothing. So 1 unit of asset is delivered to you at your expiry, so you get whatever is at ST if S is greater than K, and if S is 0, then you get 0. Okay, now let me explain the payoff for it. So for a digital option, so for our normal option, the payoff is, for a long call option, is like this. Okay, so you have, it is 0 until strike. Okay, and it linearly increases. Okay, whereas, so this is vanilla option. Okay, and digital option is, it is 0 until expiry, then it suddenly jumps to a value of whatever is agreed, let us say m, and thereafter it remains constant. Okay, so this is the example of a digital option. Okay, so this is the second kind of an exotic option. Then okay, then we have barrier options. Okay, what barrier options mean is, okay, let us say you have a stock price which evolves over a period of time. Okay, you have a stock price which is evolving as per geometric Brownian motion, right? And that is why it takes, let us say, many paths until the expiry. Okay, so it takes many such paths. Okay, in barrier option, there is a barrier which is kept like this. Okay, let us say this is a barrier B. Okay, and this is your strike K. Okay, so if it is a call, if it is a normal call option, then you will get payoffs here. Okay, and here the payoff is 0. Here the payoff is S minus K. In case of barrier option, you get payoff. So let us say the name of the barrier option is up and out barrier option. Okay, then what happens is, if the stock price goes above the barrier, then no payoff is made. Okay, so the option, the stock price, if it goes, so again there are many cases. Okay, so the barrier monitoring can be only at expiry, or it can be daily, or it can be continuous. What it means is, you will check whether the stock price crossed the barrier or not, either only at the expiry or in between. Okay, if even if it crosses one time even before expiry, then that option is worthless. Okay, and I mean, you check it end of the day, every day, end of the day, or you can check it continuous. Ever, if it ever crosses, even for 1 second it crosses the barrier, then the option is worthless. In daily cases, it is checked only end of the day. Okay, so in the middle of the day it crossed the barrier, but by end of the day it was below the barrier, then it is not worthless. And if the barrier is checked only at expiry, it means what happens in between up to expiry, it is not checked. But at expiry, if the stock crosses the barrier, then no payment is made. Okay, okay, so the payoff occurs in this zone. Okay, so let me highlight it. So this is the zone where the payoff occurs. Up and out barrier. Okay. Similarly, up and in, what it means is, payoff is made only if the barrier is crossed. Only if barrier is crossed. If it is not crossed, then no payoff is made. Okay. So all the combinations are there: up and in, up and out, down and in, down and out. Okay, for call and put. Okay, so barrier option has 4 subtypes: up and in, up and out, down and in, down and out. Okay, so all four combinations are there depending on where the barrier is with respect to strike. Okay, so these are barrier options, and then you have Asian options where the payoff is like for a normal call option, for a normal call, you have payoff as max of S minus K comma 0. For Asian, you have max of average of S minus K comma 0. Okay. So again, there are many ways to define it. Okay. Sometimes the way you define it is max of S minus strike itself is average. Okay. So whatever is at expiry minus average of whatever happened, that is kept as strike. Then you can have many kind of averages. You can have arithmetic mean, you can have geometric mean, and all of that. Okay. So you have all combinations here. Okay. Then you have compound options. So this is essentially option and option. So at the expiry of the first option, you get a choice that whether or not you want to buy the call option and all of that. Okay. So you enter into an option, the underlying of which itself is an option. Okay. The underlying starts 1 month from now, and the current option starts today. So when today's option expires, you get a choice to exercise whether or not you want to enter into a actual option. Okay. So that is compound option. And then you have chooser options that you get to choose whether you want to buy a call or put. Okay, this is similar to compound, but here you get to choose whether the underlying is going to be a call or put. Okay, so you have chooser options. Okay, so you have the Black-Scholes formula only for the basic kind of options. Okay, so you have Black-Scholes. So Black-Scholes formula can be used only for vanilla options. For all exotic options, you need to resort to some kind of simulation. It can be Monte Carlo simulation, it can be binomial tree, and so on and so forth. Okay, so you have to choose some kind of a simulation methodology where you need to evolve the stock price, and then you need to get the payoff. Okay, and then discount it and bring it to present value. Okay, any questions so far? Any questions from anyone? So what I will do is I think we can discuss about we have enough content to discuss about the project of our course. Okay, so before that, right, I want to know, like yesterday there was a form floated as to how many people would be able to dedicate enough time to complete the project, right? So did every one of you kind of fill that form and you know mm, uh, right, shared what all skills you have? I hope people have filled that form, right, for your ability to dedicate time for the project, or anybody is still left?
I have not
Everybody,
filled the form, but I will fill it after this session.
yeah, but you'd be able to dedicate time, right? Maybe a week or
Ah,
two.
yes, sir.
Yeah. So, uh, how good are you with coding skills? Good enough?
Yes, I know Python, and I'm good in
Basic.
that.
Okay. Okay. So, you are yet to be classified into groups, right? Based on your skills.
Yes, sir. The group is not formed, I think.
Uh, how should we do it? Mm, Statement and okay, let me explain the outline of the project. Okay, we can discuss still some more details. Yeah. Maybe three exotic options. Let me write the problem statement. Okay. So as part of our sessions, we have seen three methods to price an option. Okay, so namely we have seen binomial tree, then we have seen Monte Carlo simulation, and thirdly we have seen Black-Scholes model. Okay, now depending on how we are divided into groups and all, right? The group project is about the project is about using numerical methods to price an option, right? So this is okay. So I again I don't know how many set of uh, how many set of groups will be there eventually, how many people will be there per group and all of that. Okay, but okay, so group 1 So set of groups. Okay, this can be group 1, 2, whatever, right? This is set 1, and set 2 is group 2, 4, 6, whatever. Okay, so group with odd numbers, 1, 3, and all. Okay, you will do it for call option, and set 2 will do it for put option. Okay, now let us try to understand the problem statement first. Okay, before diving into it. So what you have to do is use discretization methods to numerically solve the below PDE to get price of an option. Can somebody give some thoughts? Okay, how will you do it? People on the call, can you think of something which you will do numerically, okay, to get the price of an option? Any thoughts from anyone? Think through it. Anything that comes to your mind. Okay, looking at this PDE and using it to solve for the price of an option. I'm not asking for analytical solution, no integration, no differentiation, nothing. Okay, just numerically, what will you do to get the price of an option? Anyone? Anyone on the call? Any thoughts?
Yes, sir, but no idea.
Yeah, but for example, if I give you this equation, right? What can you do with it? There is a discretization scheme, right? So there is something called as dou v by dou t, right? How can you write this as? You can write this as v at t plus delta t, right? Minus v at t divided by delta t, right? Similarly, you can write dou v by dou s is equal to v at s plus delta s minus v at s divided by delta s. Okay. Now you know what should be the price of an option at its expiry, right? You know the payoffs for each option. So let us look at this discretization grid. Okay. So let us say you start from t equal to 0. Okay. This is where you need to find what is going to be the price of your option, right? Now from time t equal to 0 to t equal to capital T, you can divide it into delta t, 2 delta t, 3 delta t, so on up to 10. Okay, so you have divided this into 10 equal parts, correct? And similarly, you have divided from 0 to, let us say, some s max. Okay, s max is 2 times of your current s or something like that. Okay, your actual s is somewhere here. You have gone further up in the chain, and you have s max here. Okay, and you have built a s by t grid. Okay, so for example, if you're valuing an option with spot as 100, okay, and you can choose, let us say, s max is equal to 2 times of s, right? So s max is 200. Okay, so you're going from 0 to 200, and then you're dividing it into equal parts, right? You are dividing it into equal parts. This is discretization of your s. And from 0 to time to expiry, let us say you divide it into 10 equal parts. Okay, and this is one of your boundaries. Okay, time to expiry is one of your boundaries. You cannot go beyond that, right? You have a hypothetical boundary here at s max. Okay, and you are bounded here by s equal to 0, right? Now, can you find what are the boundary values of it? Okay, you can pretty much find that, right? So at expiry, your option is going to take only max of s minus k values, right? So you know what values you will have here along this boundary, right? This is going to be max of s minus k. Okay, so for 7 delta minus 7 delta s minus k, it's whatever, right? This s minus k, this s minus k, this s minus k, then it becomes 0 0 0 0 everywhere else, right? And correspondingly, once it is 0, so for here also, for all option, it is kind of 0, right? The only question is what is the value at this boundary, right? So since this is at a certain level of s max, right? So let us say 7 delta minus k, right? So once it has reached a certain value, right, then your time to expiry will not have any impact, right? So your this all of these values will be s minus k, right? Now, how do you come at one point below in space and one point below in time, right? Is the question. If you get here using this point, this point, this point, and this point, it means you know how to come back to this point, right? Because you have a recursive relation, right? So you can reach this point by going one step back from here, by going one step from here, okay, and anything else if required. So you have this point, okay. Similarly, for this point, you require 3 points, which is this, and this, and maybe even this. So you can, with these 4 points, you can come back to here. Then you can come back here, then here, then here, here, and here. And like this, if you keep back traveling in time, then you can reach at this point, right? Using the same discretization scheme, okay? So your objective is to come up with the discretization scheme, right? So the Black-Scholes model, okay, roughly looks like this, correct? So v at I comma j plus 1 minus v at I comma j, where I is with respect to spot and j is with respect to time, right? So so this discretization, okay, plus half of this, okay, then you solve for vj's, right, Vij. So you rearrange this equation and you can get the value of how to come at this point, okay, using this and this, okay. And then you iteratively apply this uh, iteration going backwards in time and space and reach until this point, okay. Any questions so far? This is very important for your certificate, right? So final submission of your project is very critical. Once you are able to complete this project, only then you can kind of say that you understood what we have studied so far. We have any questions so far? Any questions from anyone? So
Sir,
yeah, go ahead.
so in the project we have to use the numerical method to price the option, na? That is the thing.
Yes.
And it could be any option, European, American.
No, it has to be European. American will be difficult. Okay. I think this will take some time for European itself.
Okay, sir.
Okay. So for example, this kind of method is discussed here. Okay, you can also follow some papers if you want. You can use your own notations and come up with this. But see, there is a discretization scheme. Okay, and how do you traverse back in time and all, they have kind of mentioned. They have typically mentioned three methods. Okay, there is a forward difference, backward difference, and there is a Crank-Nicholson method. Okay, again, Crank-Nicholson will be slightly out of scope, right? Because it's far more computationally intensive. So if you do that, there will be extra points for doing it by Crank-Nicholson. Okay, but if it takes too much of time, my suggestion is to go back to either forward difference uh, or a simple backward difference method. Okay, so what I'll do is I'll share this paper also. Where do I put it? Let me put it here. Okay, so this is what I expect. Okay, this is the basic problem statement. Let me write the deliverables. Okay. So deliverables. Okay, first I want, and there are three parts to it. There is a mathematical part to it. Okay, so whatever discretization scheme you use, derive the difference equation for, let us say, v of I comma j is equal to what? Okay, so this is the first step. Okay, so show it. So show it. So show this difference equation in your in a Word doc or PDF, preferably in a Word doc. Okay, so in a Word doc. Okay, write these steps to arrive at Vij. Okay. So this itself, so Vij is your algorithm. is your algorithm to iterate over time and spot. Okay. Second, I want a replication or implementation of algo in Excel. Okay. So have that discretization scheme in Excel, right? That you have T, delta T and all of that going up to expiry here. And one of the axis will be for space or spot. Okay. And then you go to boundaries, highlight the boundary. This is a boundary. This is a boundary. Okay. And then start recursively going back using the algorithm. Okay. Using the derived expression. Using the derived recursive expression. Okay. And third of it will be to write a Python code implementation of the same. Okay. Fourth will be to compare results for increasing discretization steps against let us say Black-Scholes model results. Okay, something which you see in this in this paper, right? So in this paper you see they start with basics and all of that, right? And eventually they implement it, calculate the price of an option using this method and compare it, right? So they have the results. Okay, so if you use X number of paths, then you get, okay, these are the prices you get and it converges to something. Okay, so and so on and so forth. Okay, so what are Black-Scholes result for different spot prices for different time to expiries and all? Okay, versus what you get as per your discretization method. Okay, so depending on whether you're in group 1 or 2, I mean even number group or odd number group, you'll be working on either a call option or a put option. Okay, so even set of groups will work on call option, odd set of groups will work on put option. Any questions so far? Any questions from anyone? So all these four things will, all these three things will be part of your submission. A Word doc, so your final submission is a Word doc. Then you have Excel. Okay, neatly labeled implementation, so that person who is looking at for the first time also understand what is happening. Okay, you cannot randomly write anything anywhere. You would color code things, your inputs, outputs. It should be neatly labeled. And third, your Python code. Okay, so well written code. I have shared a sample code yesterday, right? So try to use functions. Don't write a free flowing code. Use functions. Use correctly named variables. Don't use simply x, y, a, b, c, d. Use comments to describe what part does what. Okay, and fourth part is graphs, right? Comparison graphs. So simulation, I mean, whatever answer you get as per discretization. Okay, for various for different spots, for different time to expiries, and compared with Black-Scholes model. Any questions so far? I have shared a paper with you which describes how to do it step by step. The link to this I have shared it. You can read it, understand how to do it, and you have to you can do it the same way. You can change the notations, you can change the things as per you want, and then you can come back to your own understanding. You rewrite your own derivation for the present value, I mean the recursive relation, and then implement it in Excel. Okay. Any questions from anyone? I'll just take a pause for 30 seconds. Meanwhile, I'll export all of this to our final project. And I'll share all the other things which we have discussed today. Exotic options, QF course. These are the notes. PDF. Black-Scholes and Greeks. Any questions from anyone? So that's why deliberately I'm not given any assignment for this week. So we'll pretty much cover most of the things which you have covered as a part of project. Okay, it looks like nothing else. So maybe we can close this call. Right. Let us connect for our doubt session the next week. Thanks everyone for joining. Bye.
Bye, sir.
Bye, sir.